A very good afternoon to one and all present here. Today we are here to celebrate the Foundation Day of SN Bose National Center for Basic Sciences. My name is Prapti Mukherjee. I'm an integrated PhD at the center. SNBN CBS is an autonomous research institute established under DST, Government of India, in the year 1986. It was established to honor the glorious life and work of the legendary Indian physicist, Professor Shotendranath Bose, who was a remarkable theoretical physicist and had significant contribution in the field of quantum mechanics and quantum statistics. Since its inception in 1986, the center has been an important destination for fundamental research in the field of physical sciences and interdisciplinary fields. The Institute has been through a spectrum of changes and scientific contributions since its beginning. We can never forget the remarkable scientist, Professor Chanchal Kumar Majumdar, who happened to be the first ever director of the center. Today we are here to celebrate the foundation of this beautiful place, which has been witness to important scientific contributions and developments.
সকলকে স্বাগত এবং অভিনন্দন। প্রফেসর এস.এন. বোস নিঃসন্দেহে বিংশ শতাব্দীর একজন অন্যতম উজ্জ্বল বিজ্ঞানী। তার পাশাপাশি তিনি একজন দায়িত্ববান এবং সহৃদয় শিক্ষকও বটেন। তিনি বলেছিলেন, we wanted to put some scientific knowledge to the use through the technology for the benefit of the people and to contribute to the science by intensive study. তার এই স্বপ্ন পূরণের অঙ্গীকার নিয়েই 1986 সালের 13ই জুন প্রতিষ্ঠিত হয়েছিল আমাদের এই এস.এন. বোস ন্যাশনাল সেন্টার ফর বেসিক সায়েন্স, যার বৈজ্ঞানিক উৎকর্ষতায় আমরা আজ গৌরবান্বিত। আমরা সকলে এখানে আজ সমবেত হয়েছি তারই প্রতিষ্ঠা দিবস উদযাপনের জন্য। আমরা জানি যে এই প্রতিষ্ঠানটি প্রথমে কলকাতা রিসার্চ সেন্টার অফ বেসিক সায়েন্স নামে পরিচিত হলেও পরবর্তীকালে ভারতীয় পদার্থবিজ্ঞানী প্রফেসর সত্যেন্দ্রনাথ বোসের সম্মানার্থে এটির নাম এস.এন. বোস ন্যাশনাল সেন্টার ফর বেসিক সায়েন্স রাখা হয় এবং তারপর দীর্ঘ 37 বছর ধরে এই প্রতিষ্ঠানটি ভারতের অন্যতম নেতৃস্থানীয় গবেষণা প্রতিষ্ঠান হিসেবে আমাদের দেশ এবং বিদেশের বিভিন্ন গবেষক বৈজ্ঞানিকদের আকৃষ্ট করে আসছে এবং কিছু মেধাবী স্টুডেন্ট অর্থাৎ ছাত্রছাত্রীদের বারংবার সম্মানিত করেছে। এইভাবে যাত্রা আরো এগিয়ে যাক, এই কামনা নিয়ে আজকের এই অনুষ্ঠান আমরা শুরু করছি।
Today we have with us a number of eminent. I'm sorry for the interruption. Today we have with us a number of eminent guests. To say, Ms. Nandini Priyadarshini Bose, granddaughter of Professor Shoten Bose, Professor Arup Kumar Rai Chaudhuri, former director and remarkable scientist, Professor Partho Ghosh, eminent physicist, author, philosopher, and musician. Dr. Indranil Shannal, Director of the Northeast Zone of National Council of Science Museums. Mr. Shunish Dev, former DR academic of the center. Professor B.N. Jagtap, Professor of IIT Bombay and Chairman of the governing body of SNBN CBS.
Now I would like to request our honorable guest, Professor B.N. Jagtap, IIT Bombay and Chairperson Governing Body SNBN CBS, to kindly inaugurate this auspicious occasion.
Yes, what do I do?
Professor Jagtap, are we audible?
Oh, yes, I can.
Yeah, so we request you to inaugurate and say a few words.
Okay. I thought there is something else for the inauguration. Thank you very much. Professor Tanushree Shahadas Gupta, Director of the Center, the Deans, HODs, faculty members, registrar, administrative staff, students, very, very distinguished invitees, ladies and gentlemen. At the outset, let me greet you all on the occasion of the 37th Foundation Day of this center. Foundation Day is a very special day when we fondly remember the vision of our founding fathers, the commitment of the faculty members of our academic excellence, the dedication of our non-teaching staff, and the passion for learning of our students. The center has been doing exceedingly well in cutting-edge basic science, basic research with high standard publications and also generating very valuable human resource. Many of you have received awards, honors, and accolades from national and international agencies. I take this opportunity to compliment the director, faculty, staff, and students on their continued efforts to make this center a place for advanced learning in the country. On this day, let's rededicate ourselves so as to take the institute to still bigger heights. I am extremely happy to see that the center has instituted token awards to appreciate best efforts by faculty members and students, as was recommended by the governing body. Wishing you all very best in your future endeavors. Thank you, one and all.
Thank you so much, Professor Jagta, for your encouraging words. May I now request Professor Tanushree Shahadas Gupta, our respected director of the center, to say a few words and hence give the welcome address.
A very good afternoon, ladies and gentlemen, all the distinguished guests present in the audience, as well as my dear faculty members, staff, and students. It's a very happy occasion to celebrate the 37th Foundation Day. So we have completed a journey of 37 years, which started in the year 1986. And we started in a rented house and with a handful number of faculty members and students. You know, from that stage, the center really has reached in a remarkable time to a remarkable height. Now the center has its own campus with several buildings. The student strength has reached about 180, and our academic members, including the permanent faculties as well as the postdoc, the PhD inspired Ramalingam, Ramachami, all this has really increased the academic capability of this center in a remarkable way. In last few years, actually, the center has signed up MOU with various national and international institutes. The worth mentioning is with IFW Dresden in the area of quantum materials, which is one of the focus of this institute. And I'm very happy to say currently 3 of our PhD students are spending time there in the collaborative research, and we do feel that there will be fruitful outcome of that. The center has signed MOU with IIT Bombay in the area of soft and hard condensed matter in terms of sharing students and sharing resources. With the Presidency University, which is a new venture of us, especially in terms of collaboration of manpower training, with Shidu Kanu Bishra University in the area of observational astrophysics, because we have actually an observatory that is planned to come up in the area of the Panchit Hill. The other worth mentioning is the establishment of the supercomputing hub. We have signed the MOU with the CDAC, which will cater the computational need of Calcutta and surrounding SN Bose Center being the hub and the nodal center of that. So these already tells in, at least in last couple of years also, this growth has continued. And I'm very much confident that in future, there will be only upturn and no downturn at all in our map. And we have a rather packed program, as you have already seen in the program. The first in this list is the virtual tour of the Bose Archive. The Bose Archive was established in the year 2002, where actually it was inaugurated by none other than General Shankar Bose. That's what I found, Shankar Rai Chaudhary, I beg your pardon, on 4th July 2002. And that had only 5 display racks covering various aspects of the life and work of S.N. Bose, with a collection of letters, pictures, and personal belongings, which were actually very kindly donated by the Bose family. The present archive was further get modernized and designed in a better way and implemented by the National Council of Science Museum, and was inaugurated by January 1st, 2080, which was happened to be the 125th birth anniversary of Professor Shobhendranath Bose, by then Science Minister, Honorable Minister Dr. Harshvardhan. On 1st January 2020, this new version of the Bose Archive has been made open to the public. Since then, we actually received a lot of requests for visiting the Bose Archive. However, it is not possible for a scientific institution to keep this thing open to the public all the days without hampering any of our activity. Although we have made a special attempt that, starting a couple of years back, we have an open day in the month of January, which is widely advertised in newspaper, and anybody can come and see the Bose Archive on that particular day. But to make it more accessible, we have made this virtual tool so that just with one click, you can have a tour and can see at your own pleasure this really very nicely made Bose Archive. So this virtual tour, which has been created by Pure Pixel, Mr. Shampan Das, Sandipan Das is present from Pure Pixel, and they took the lead in making this virtual tour. And you will find when it is played that there are some extra information beyond what is there in the panel. By clicking that, you can get that extra information. And that was compiled by our science communicator, Ms. Shubha Dasmalli, with the help of Mr. Shantan Mukherjee, who helped in designing some of these. So I do hope you will actually like this virtual tour. And if you don't have enough time today, later on at leisure, you can also make an experience of this virtual. Then the next in our program is the talk by Dr. Manik Puni, who has joined S.N. Bose Center very recently and already have shown a great promise. So from him, I hope we will hear about the recent status of the quantum information theory, and which will be followed by a tea break, and then there will be a few award ceremony, as our Honorable GB Chairman has mentioned. We have now instituted this recognition for the excellence in teaching to basically encourage more and more faculties to get engaged in the teaching, as well as awards will be given to the toppers in the IPHD. We had this practice, but somehow it was discontinued in the middle, so we'll revive that. And that will be followed by a cultural program. S.N. Bose, as you are all aware, was actually a great lover of music, and especially the classical instrumental music. He was a great estrade player. So keeping that in mind, we will end our evening today with this beautiful musical journey, which will be performed by the very accomplished sitar player, Sri Kullan Majumdar, who will be accompanied by in tabla by Sri Ashok Mukherjee from the ITC Sangeet Research Academy. So I do hope that you will enjoy this Foundation Day celebration. And once again, welcome to all of you to this evening. Thank you.
Thank you, ma'am, for your valuable speech. Now, we would like to call our respected Sir Rajiv Mitro on stage and to continue the entire program.
So we start with the attendance ceremony. So I request our director, Professor Tanushree Shardas Gupta, to kindly come to the stage and do the attendance ceremony.
I just click here. So it's the curtain raising for the virtual.
very nice commission from our archive. Before proceeding to our further talks and other events, we are very privileged to have Professor Partha Ghosh with us. So maybe I request Professor Ghosh to say one or two words on this occasion. So please.
You want to give your impression.
Good afternoon, everyone. It's a great pleasure and honor for me to be here on this occasion. I had the rare opportunity of doing my PhD under the great man. And then after this institute was established, I soon had the honor of being a faculty member. So thank you once again, Tulasi, for inviting me to this occasion. Having said that, let me say that as your director told you, the archive started in a very small way, but now I can see it has really grown. And it's been presented in a very, very nice way, taking advantage of digital technology. And I very much hope that more people will see it. It's not necessary after this that people come here physically. See, you may try and promote it through the digital media. I personally like the program very much. Thank you so much. And I wish that it's really promoted well, because S.N. Bose and his work really needs to be known more widely, although the word Bose and bosons are part and parcel of our lives as physicists, but somehow, possibly because he left Europe too quickly, he somehow did not get the recognition that he deserved to in his lifetime. More recognition has come later, but that's all right. So I hope the S.N. Bose Center really takes up this program in right earnest. Thank you so much.
So now we move to our next class. Let's talk by Professor Manik Pradhan. So let me have the pleasure to introduce Manik to you. So apart from being a very good friend of mine, he is actually a very accomplished theoretician also. And for record, he did his bachelor's and master's from Jadavpur University. His PhD is from ISI Kolkata. And then after his postdoc, he joined his center as an expert. Then he joined this ISI Trivandrum as a faculty, and thankfully he has come back to Kolkata. And I actually love, apart from scientific discussion, many more discussion of political and social aspects. Today, I think he will be talking more on the various Euclidean and the experiments of it. So,
hello, am I audible? Yes. So, good afternoon, everyone, and welcome once again to Foundation Day program. So, in this Foundation Day program, since our center name is by Professor S.N. Bose, who is one of the founder father of quantum mechanics, I have decided to talk about one of the foundational issues regarding quantum mechanics. So I have chosen the title of my talk to be "The Nature is Non-Local Ultimately." I hope at the end of the talk I'll be able to give a sense what I mean by this. So probably many of you know last year Nobel Prize in Physics is given to these three scientists, Alan Aspect, John Georgia, and Anton Geilinger. And Nobel Committee, it has written, but they have given the Nobel Prize for experiment with Denfinger's photon, establishing the violation of Bell inequalities and pioneering quantum information science. So today in my talk, the motivation will be to understand why violation, what we mean by violation of Bell inequality and why it is at all interesting or important. So I'll start by 1 2-minute slide talk by Professor George Bernard Shaw. It is a talk in 1930 in honor of Albert Einstein.
Today dinner in London in honor of Professor Einstein. There is always great deal of speech. If you take the typical great man of our historic epoch, and suppose that I had the right here tonight to propose the toast of Napoleon, well, undoubtedly I would say many very flattering things about Napoleon. But the one thing which I should not be able to say about him would be perhaps the most important thing. And that was that it would perhaps have been better for the human race if he had never been born. Napoleon and other great men of his time, they were makers of empire. But there is an order of men who get beyond that. They are not makers of empires, but they are makers of universe. When they have made those universes, their hands are unstained by the blood of any human being on earth. Solomon made a universe which lasted 1400 years. You also made a universe which has lasted 300 years. Einstein has made a universe, and I can't tell you how long that will last.
So, okay, the talk was in 1930. I don't know if George Bernard Shaw writes today probably he could replace the name of Napoleon by many other people. You don't know, you know already. But that is not our discussion today. I'll mainly focus on this last 3 sentences. He pointed out Ptolemy made a universe which lasted 1400 years. Newton also made a universe which has lasted 300 years. And Einstein had made a universe, and he has some doubt that how long that universe will survive. So what are these universes? Let us try to have a look from a historical perspective. What is Ptolemy's universe? So Ptolemy's universe was a geocentric universe. Earth was at the center, and all stars, planet, everything moves around this Earth. And this idea, today we know it is wrong, it is not correct. But this idea was at least survived more than 1 millennium. And up to when it is contested by few observations, by few inquisitive minds like Nicholas Copernicus, Tycho Brahe, Bruno Galileo, then this idea of Ptolemy's universe was challenged. And finally, Newton come up with this famous universal law and give us a new word. This is Newton's word. So this famous Newton's equation. But there is some issue with Newton's universe. Gravity in Newton's theory, however, appears to be a non-local force and allow instantaneous return. Means in Newtonian theory, if I change the mass here, mass distribution here, its effect throughout the universe is instantaneous. This is very peculiar. Even Newton was bothered about this peculiarity of his theory. if you look into his code, the gravity should be innate, inherent, and essential to nature, so that one body may act upon another at a distance through a vacuum without the mediation of anything else, by and through which their action and force may be conveyed from one to another. It is to me so great and absurd it is no man who has in philosophical matter of competent faculty of thinking can never fail into. Gravity must be caused by an agent acting constantly according to certain laws, but whether this agent be material or immaterial, I have left to the consideration to my readers. So Newton doesn't have answer to this question that how gravity force works. So this was Newton's universe. It survived 300 years. Why it survived 300 years? Because it's a non-local universe. Instantaneous signaling is allowed in this world. Nearly 300 years later, the great Einstein came. Einstein makes physics local. So what is one immediate consequence of special theory of relativity? It tells us that if causality to be preserved, no information signal or material object can travel faster than light in fact. So now physics is local. Any effect, any information cannot travel infinite velocity. It has a fundamental upper limit of speed. That is the velocity of light in vacuum. And within 10 years of the special relativity, Einstein succeeded in producing an alternative theory of gravity, general relativity, which obeys the principle of locality and provides a material account of how gravity works. So this is Einstein universe, and probably George Bernard Shaw has some doubt, okay, how long this Einstein new universe will survive. So when Einstein was actually building this theory, his beautiful theory, at the same time another story was going on. Professor Satyen Bose was also one of the part of that is the birth of quantum mechanics. And historically, birth of quantum mechanics actually comes from some observation that cannot be explained within our known classical language. By classical language, I here means Newtonian physics, and for wave case it is Maxwell theory. So first matrix mechanics by Heisenberg come, then wave mechanics by Schrödinger, and then it has been shown that these two are equivalent, and finally this has been more compact form it is coming. So principle of quantum mechanics is one of the very famous book by Dirac, and one of the first mathematical foundation is by John Conway. So now we have a quantum theory, very successful theory. So does the story end here? This is our question. What do we mean by quantum mechanics? Work perfectly for all practical purpose. So for all practical purpose, John Stuart Mill, will come to him, who is John Stuart Mill. He sometimes call it this phrase, FAPP. So quantum mechanics is actually working very good. But wasn't there more to physics than FAPP? In other words, at the end of the day, after all the wave function has been calculated and probability is plotted, shouldn't quantum mechanics have something coherent to say about nature? And this question was actually bothering even the founder of quantum mechanics. Who invented quantum mechanics, they were also thinking about this question. And the debate was going between Einstein as well as Einstein and Bohr. Einstein, Schrödinger, Bohr, Heisenberg, all were involved in this debate. And during this debate goes for a long time. In 1935, Einstein actually came up with a very beautiful argument to show some limitation of quantum mechanics. This is a very famous paper. Nowadays it is known by EPR paper or EPR argument. So historically, this was published in 1935, and there is a very historical interesting fact also to look into the date. It was published in May 15. On the other hand, May 4, New York Times published an article that Einstein attacked quantum theory. Scientists and two colleagues find this not complete, even though correct. But Einstein was very irritated by this article. But it is quote, any information upon which the article Einstein attacks quantum theory in your issue on May 4 is based was given to you without authority. It is my invariable practice to discuss scientific matters only in the appropriate forum, and I deprecate advance publication of any announcement in regard to such matter in the secular place. Okay, why does that? That is not our today's discussion or debate. But let's try to understand very intuitively what we are trying to say. In this slide, what is written, everything I am actually quoting from their paper. What they say, in attempting to judge the success of a physical theory, we may ask ourselves two questions. Is the theory correct? Is the description given by the theory complete? And if we was not questioning about the correctness of this quantum mechanics, it is the second question that we wish to consider here as applied to quantum mechanics. So now the question is, what do you mean by completeness of a theory? What they say? What about the meaning assigned to the term complete? The following requirement for a complete theory seems to be necessary one. What is the requirement? Every element of physical reality must have a counterpart in the physical theory. So then, okay, this is the necessary requirement for complete. Shall be satisfied with the following criteria, which we regard as reasonable. And what is that criteria? See, if without in any way disturbing a system, we can predict with certainty, that is with probability equal to unity, the value of a physical quantity, then there exists an element of physical reality corresponding to the physical force. So we can predict a quantity without disturbing it deterministically, then that is the property of the system. And this property theory must be able to explain this physical reality. That is their default. So with this criteria, with the criteria of physical reality and completeness, they proceeded to show some limitation of quantum mechanics. Let's try to understand how they are trying to say. So here I am discussing, it's not the actual EPR paper, it is a simpler version by David Bohm. So you can thought about an experiment. So there is a source, it emits two particles, one particle goes to Alice and another particle to Bob. And let's assume that Alice and Bob are first separated. How far? Okay, since it's a theoretical thought experiment, you can imagine Alice and Bob are extremely far. Let's say one is here and Bob is let's say 4 light years. So now quantum mechanics, according to quantum mechanics, which is already a developed theory, we can prepare a state which is something like very peculiar kind of state. It's called nowadays we call it an integral kind of state. But what is the property? If we do some experiment, some peculiarity comes. Let's try to see. If Alice performs spin measurement along z direction on her particle, and if he obtain outcome 0 or R, immediately she can say, okay, Bob's z outcome will be 1. At the same time, if Alice got outcome 1 or down, immediately she can say if Bob performs z measurement, her outcome will be up. So now, you see, without disturbing Bob's system, she can predict the value of z measurement perfectly. Why we are saying without disturbing the Bob system? Because any disturbance, according to locality, requires some time to propagate. But before that, Alice can actually predict the outcome of Bob. So, according to their definition of our criteria of physical reality, measurement along z must have a physical reality. Okay, so far it is fine. But this state is very peculiar. We can actually express this state in a different way. And we can perform a spin measurement along a different direction. And this time let's consider x direction. The same argument in our earlier slide what we have argued, we can similarly argue that sigma x measurement should also have a physical reality. But that is not all. The completeness demand is both sigma x and sigma z should have physical reality. But there's the problem. The quantum mechanics now say you cannot have a common eigenstate. You cannot jointly know this sigma z and sigma x. So in quantum mechanics, it is usually assumed that the wave function does contain a complete description of physical reality of system in the state to which it corresponds. However, this assumption, together with the criteria of reality given above, leads to a contradiction because they cannot be simultaneously known, this value of sigma z and sigma. So what is their conclusion? Einstein-Napier conclusion? They say, okay, quantum mechanics is a very correct theory, but its description is not complete in the sense what we have defined, introduced. And that is very common sense definition or criteria also. So while we have shown that the wave function does not provide a complete description of physical reality, we left open the question of whether or not such a description exists. So they raise a question and open it, put it challenge to the next generation. And also they make a comment, we believe However, that such a theory is possible. So then the question is, okay, let's try for that theory, whether it is possible or not is possible, how to come up with that. So unfortunately, from 1935, this direction, foundational question, it was not that much debated or discussed due to some reason, maybe Second World War or some other issues are there. But interesting breakthrough comes in 1964, and it is by John Stuart Bell. Who was John Stuart Bell? He was a physicist from Northern Ireland. And Bell's career began with a UK atomic energy research establishment. In 1960, he moved to work for the European Organization for Nuclear Research, CERN, in Geneva, Switzerland. There he worked almost exclusively on theoretical particle physics and on accelerator physics, but found time to pursue a major avocation, investigation, the foundations of quantum physics. In his term, his language, I'm a quantum engineer, but on Sundays I have principles. So during his leisure time, he used to thought about this question. So there was some unresolved question was there regarding foundation. And if you see at that time, Bell's paper, which was published, was not published in that much prestigious journal. But later time, people have identified these are really very important work. And nowadays, it is available in a book format, very well-known book, speakable in quantum mechanics. So what John Stuart Bell trying to answer? He actually trying to address the question EPR posed. So EPR was actually thinking about such a thought experiment, that Alice and Bob were separated. Alice performed some measurement on her system, Bob performed some measurement on his system. And let's very simple-minded, Alice choose one among two possible measurements, and Bob also choose one among two possible measurements. And each measurement have two outcomes. We can make more complicated scenario, but for the sake of our argument, the simplest scenario is sufficient. Let's denote A and B the measurement outcome of X and Y measurement. And let's say some hypothetical hidden local variable theory was what Einstein EPR was thought about or dreaming about that exists, and let's denote it by lambda. And this lambda are hidden in the sense, why you call it hidden? It's nowadays in philosophical community, it is called sometimes ontic state. Ontic means it is the actual state of the physical system. Or in foundation community, more popular term is hidden. Why it is called hidden? Lambda is hidden in the sense that they are not a part of quantum theory. So quantum state can be a part of lambda. Okay, this is much more technical thing that is not required for us. So the experiment of this, finally experiment, this simple experiment, everything we can describe is nothing but the joint probability. Because we will do this experiment many times, we will collect the statistics. So this is the conditional probability. So what this probability means? The probability that Alice obtain outcome A and Bob obtain outcome B, condition that Alice perform measurement X on her system or perform measurement Y on his system on the state lambda on the system prepared on the state lambda, which is hypothetical local hidden variable. We don't know this lambda. But what is our demand? Our theory should be local. That was the Einstein dreaming about. So if we put this condition at this lambda level, it turns out that this joint probability statistics actually breaks down this factorial. So this is sometimes called locality or Bell locality condition. Now there is a few line algebra, very simple algebra. I'm not going into details. Using that, Bell actually show that, okay, there is an expression, this expectation value of x0, x1, x0, y0, x0, x0, y1, x1, y0, x1, y1. If we calculate this expectation value and this finally this expression, if it is the case that this lambda is factorized like that, then the value should be bounded by 2. And what is this expectation is calculated? This is defined. So now they have a criteria, because if you look into the left hand side, it is experimentally testable quantity. We can go to lab and experiment to the experiment. So now what Bell is showing, if we assume our world is local realistic, then this experimental quantity should be bounded by 2. Now let's say we go to do this experiment and we obtain the inequality is violated. We are getting value more than 2. What should be our conclusion? Our conclusion that what assumption we start with, that is not possible. And Bell actually shown there exists quantum state, the same state if we are used, or if we have discussed in Bohm argument, using the same state, mathematical calculation is showing us, yes, we can go up to 2. So there is a way at least. The same, the 1935 philosophical question, what Einstein was asking for, the possibility of a theory, there now is a way to test that, whether nature satisfies local reality or not. But this is so for all the theoretical data. It might happen, okay, what quantum mechanics we are doing, this is not correct, this is our mental construction so far. It might happen, nature doesn't allow such a state. So the question actually boils down to, can we prepare such a state and actually get violation in lab? That is much more challenging task. And scientists, Roger Geilinger, they take this challenge for few decades. The experiment you see started from 1969 and a series of experiments, and all these experiments actually showing with certain degree that yes, the inequality is violated. So the dream APR was showing, thinking that okay, that is a possibility. What this, if we believe that such a theory is possible, that it is indeed not possible. So let's come to the conclusion. So in Bell's theorem, lambda denotes the state of system as described by any possible future physical theory. In this sense, Bell inequality go way beyond quantum theory. What is the fundamental conclusion from Bell inequality violation? The violation of Bell inequality proves that no future theory can satisfy the locality condition. But you see, Bell inequality is so simple. It's all the derivation we can actually discuss with this class 12 student. But the problem is in interpretation is many a time it is misinterpreted. Even when Nobel Committee is giving this prize, what they are telling, let's see. Despite being elegant and simple, Bell inequality is often understood incorrectly. For instance, consider the scientific background provided by the Nobel Committee. A few lines after correctly presenting Bohm non-local hidden variable model, one reads that Bell inequality violations show that no hidden variable theory would be able to reproduce all the results of quantum mechanics, which actually just contradict what they say. They first describe the hidden variable theory and they say, okay, Bell's theorem proves no hidden variable theory is possible. Actually, the correct statement should be, no local variable theory is able to reproduce all results of quantum mechanics. All the debate, all these things is just only for a single word, local, whether our universe is local or non-local. But when they are interpreting, they miss this one. Not only that, after a few lines, further, they say, okay, locality is defined to be no signal, no communication without any physical object carrying the information. Despite the fact that one of the main contribution of quantum information to the foundation of physics is a clear distinction between these two concepts, locality and communication. This is the fundamental concept. Of course, it is much more technical. I am not going here in detail. So what I am trying to say, Bell's inequality is very elegant, very simple, but there is a lots of scope to misunderstand. Final remark, on the conceptual side, the violation of Bell inequality dramatically revolutionized our worldview. Newton's theory of gravity was non-local. Not only that, even signaling. But Einstein improved on it, making gravity local. It is thus not surprising that he strongly objected to quantum non-locality, not fully appreciating that it is of a very different sort. The non-locality in quantum mechanics is a completely different than non-locality in Newtonian world. Without any action at a distance. Non-locality in Newtonian world was allow you to faster than like instantaneous communication. But this quantum non-locality doesn't allow us to do that. Without any action at a distance, just non-local randomness, without any possibility to use it for signal. So how long Bell universe or this new worldview will last? If nowadays George Bernard Shaw posed this question to us, because he was doubtful to at least Einstein universe. Now we have a new universe, Bell universe. In contrast to Newton non-locality, quantum non-locality is here to last forever. At least the experiment suggests that. Because finally, Physics is nothing but a theory of experiment. We have to, everything we have to conclude from experiment. All the experiment performed, here I have listed around 10 to 12 experiments up to 1999, but even after that, more than 10 to 15 groups run differently this Bell experiment with different setup. All the setups suggest that Bell inequality is violated. So it is to last forever. It might happen that, okay, you know that quantum mechanics is very successful theory. Of course, so far we cannot include gravity and quantum mechanics together. It might happen. There are lots of possible proposals. It might happen quantum mechanics we have to replace by some broader general theory to incorporate the phenomenon of gravity. But even then, at that time, non-locality will remain, because the non-locality established by aspect closure and Zeilinger experiment, that is not about quantum mechanics, that is about nature, because this is the experiment. That's why in the title of my talk I put the nature is non-local ultimately. So I have shown you 4 universes. Ptolemy's universe, then comes Newton universe, then comes Einstein universe, and then comes finally Bell universe. Why I put all these things? Because these are some paradigm shift discovery. This completely changes our world. And whenever some paradigm shift discovery comes, there is enormous possibility to new application. And Bell's theorem, Bell inequality also opens up possibility of lots of new applications. Today, non-local quantum correlation are explored for device-independent quantum information processing, a truly fascinating research field, unthinkable before Bell's work. I'm not going into the details of this. It is only a starting point of this new information era. We even don't know present day what our other possibilities are there for non-local correlation. I end my talk with 2 quotes, one by John Bell and one by David Marmin. What Bell said, for me it is so reasonable to assume that the photons in those experiments carry with them programs which have been correlated in them, telling them how to be. This is so rational that I think that when Einstein saw that and the other refused to see it, he was the rational man. He means Einstein was the rational man. The other people, although history has justified them, though experiment now support them, were burying their heads in the sand. So for me, it is a pity that Einstein's idea doesn't work. The reasonable thing just doesn't work. Reasonable means our classical or old classical. So what David Marmin said, what makes the pursuit of science so engrossing is to learn that one's most strongly held beliefs can be completely wrong. The search to identify and correct the old errors can lead to deep insight into nature. The world would be a far better place for all of us if these joyous scientists find in exposing their own misconceptions were more common in other areas of nature. With that, thank you for your patience, and if you have any questions.
Thank you, Vani, for this wonderful talk. Maybe I take one.
Yeah.
Anyone is interested in this question? Yeah, so.
Thank you very much for a very, very interesting talk, very clear talk. I would just like to point out one thing. Experiments are experiments, and good experiments, experimenters know how to do the experiments properly. Question is the interpretation of the experiment. And there I think there's still scope for doubting that non-locality of the type that you mentioned is here to stay forever.
Yes.
Because there are other interpretations of quantum mechanics, like, for example, cubism, which strongly disagrees with this interpretation.
Yeah.
Because the assumption of reality may not be true. Reality of the kind which Einstein had in mind may not be true.
Exactly. So if I just add with your point, so you see in Einstein reality definition, we are working with that paradigm.
Yeah, but that,
If without disturbing a system in bracket, that is with probability 1, we can predict something. Now, if I say I can predict some outcome with some probability, immediately I say, okay, this is my subjective ignorance. But once probability is 1, I start calling it objective. It should be true for all. That is Einstein actually taking as definition of real. But these cubism people, they're actually attacking that. Why you are taking even probability 1 to be objective nature. So that debate probably Bell's theorem is not addressing that question. So if your definition of objectivity is different, everything, again, being a student of science, you should be open to that. And there are very recent times, there are very discovery regarding this Wigner-Friend paradox, all this subjective of objective interpretations.
One more comment, if I may.
Sure, please.
Shortly after Einstein's paper, Bohr wrote another paper with the same time.
Yes,
He agreed with Einstein's arguments, but disagreed with his conclusion.
yes. But I
Simply because instead of saying the nature is real in the way Einstein was, if you say that it is contextual, that is, the result depends on it,
yeah.
then the same things can be explained, and you don't need to invoke.
Yeah,
knowledge
but probably contextuality now we have some more precise meaning after Kochen and Speaker. Probably problem is Bohr's paper, even the question how Bohr was challenging Einstein, it was not nowadays how precisely these cubism people are making. Bohr, it was just an intuition, it was not precise what he's telling. He has some feelings. But now
I
cubism
may
people,
propose, can we continue it over the
Yeah,
coffee break?
so-
Because this is the ideal thing to continue over.
Okay, so we'll break for a coffee and come back at 4:35. Okay. Okay, so welcome back to this second session of this session, and we start with the prize distribution or distribution ceremony. So we first request our director, Professor Tanushri Shahdas Gupta, to kindly present the award for excellence in teaching. So, Professor Shahdas.
So I think we have come to an exciting moment in the sense that it's full of suspense. As per the recommendation of governing body and very pertinent recommendation to encourage the teaching activities of the sector, because manpower training, I think, is based on the teaching. Until and unless you have a good trained manpower, the next part of the training, which happens during actually the PhD research work, remains incomplete. Unless the foundation is strong, you cannot be a good researcher. So keeping that in mind, from this year, we have basically instituted a recognition for the excellence in teaching. And this is entirely based on the student feedback. And from now on, after every semester, actually, the student feedback will be taken. So it's based on the student feedback. I have actually some names. And as it looks like that, to be fair, we need to honor not one person, but two teachers. So the first one, I think many of you can guess, is Professor Amitabh Laidi. That is the award, which is looking and the second name is that of Dr. Shuman Chakraborty. It's up by maybe little. Now the choice.
So now we will be presenting prizes to the first rank holder of the IPSD program starting from 2018. So I request our Dean Faculty, Professor Anjan Borman, to kindly present the first two awards. So the 2018 first rank holder, Anvesha Chakraborty. Uh, 2019 it was Partapati Mahanto Mahapatra, but he is not here. So for 2020 it is Animesh Hazra. Now I request our Dean Academic, Professor Amitabh Lahiri, to present the next two awards. Uh, 2021 is Shoham Sen. And for 2022, it is Sudhir Chakraborty. Thank you, Professor Borman and Professor Lahiri, for presenting the award. So finally, we come to the last end of this program, and we will have this cultural program. But before that, I think they will introduce the today's program and the performers.
Okay, so it's time to conclude this joyous day on a musical note. We will be having a performance by Mr. Kullan Mujumdar from ITC SRM, who had been playing the sitar, and Mr. Ashok Mukherjee from ITC Shongit Research Academy as well would be accompanying him on tabla. Please, a big round of applause for them.
I would request Director Ma'am to please come and felicitate the artist.
A very good evening to all. And my regards to all the professors sitting here and of course all the students and all the members of the audience. It gives me immense pleasure to be a part of this evening's recital. And I will start with a short recital of the timeless Rag Yaman and then continue on to something a bit more mass oriented, if I may say, that some Rabindra Sangeet and a fusion of classical music with Rabindra Sangeet, how we can do it. And but first of all, we start with Rag Yaman and short alap along with Chaptal and Tinta. I'm happy to have Ashok Mukherjee of Tabla with me today. And of course, a big thanks to this esteemed institute and also ITC Sangeet Research Academy, who has given us the opportunity to perform here. I will not speak anymore and directly go into the performance. Thank you so much. The next composition that I'm about to play in Rag Yaman is a well-known composition that I think many of you would know, not through classical music, but through Coke Studio. This is Ao Balma, a famous composition, which was sung in Coke Studio by Ustad Ghulam Mohammad Khan sir and A.R. Rahman, of course. I'll try to play that in Rukita. Thank you. Do I have time? Okay. So I would like to conclude the program with some classical music fused with Rabindra Sangeet, because everybody might not understand or fathom classical music in its full glory. So mixing it with some popular tunes to enhance the reach, that I would say. So I would just like to present Rag Desh with very popular Rabindra Sangeet Kishore Shyamala Sundaro in a classical music format, but keeping the rag intact and also the song intact. Let's see. Thank you so much. Thank you so much.
Thank you very much for this wonderful performance. And like everything, every good thing, this also comes to an end. Celebration of the day. So thank you everyone for being with us. Thank you very much. Thank you.